Everyone, welcome to chapter 9. Chapter 9 is the continuation of chapter 8. So everything pretty much that you went over in chapter 8, we are going to be extending to chapter 9. In chapter 8, we talked about one proportion, one mean, one standard deviation, and one variance. In chapter 9, we are going to do inferences from two samples. So now instead of, in section 9.1, we are going to be doing two proportions. So we're going to have hypotheses dealing with P1 hat and P2 hat. So now it's going to be two proportions. 9.2, two means, two dependent samples, and two variances and standard deviations. Again, we are going to be using StatDisk to help us solve for finding the p-scores, for finding the z-standard, the z test. Is it in the region, outside of the region? Are we going to reject or fail to reject? So everything, it's extending to two proportions, two means, two dependent samples, and two variances. And that is going to be chapter 9. So let's begin on 9.1. In this section, we present methods for testing a claim. So we're going to be testing a claim. Again, we're going to be doing hypotheses testing about two proportions. We are going to be creating a confidence interval to estimate the difference between two population proportions. And then we are going to be looking at the probabilities or decimal equivalents of percentages. So the objective is to construct a hypothesis test of a claim, and then also creating a confidence interval for estimating the difference between two population proportions. So we're going to be P1 minus P2 hat. So we are going to be constructing a confidence interval. We're doing two things at once. So we begin by identifying the notation. What notations do we need? What do we need? We will need P1, which is the population proportion for the first population, P1 hat, which is the sample proportion. It's the number of successes over the total sample size of the first sample. So we're dealing with two samples at the same time. And then we have Q1, which is one Q1 hat, which is 1 minus P1 hat, the complement of P1. And the same thing is going to go for P2, N2, X2, P2 hat, and Q2 hat, which is going to apply to the second. So what we're going to do in this section is we're going to have two different samples coming from two different proportions. We're going to deal with P1 and P2, and then we're going to look at the differences between those two. In order for us to look at two proportions, there exists something called the pooled sample proportion. That's where they kind of both of them mix. And then there exists this pooled sample proportion denoted P bar. This is P bar, which is a combination of the two sample proportions. So we must take into consideration the pool sample proportion in this case. Okay. So the sample proportions are from two simple random samples. They are independent samples, so they're not related somewhere. They don't have any combination whatsoever. So first, they must be simple random, they must be independent, and the two of them must have at least 5 successes and at least 5 failures independently. So you have to have N times P hat greater than, this is for each of them. So we have to test both samples, sample 1 and sample 2. They both must satisfy this requirement, at least 5 failures, at least 5 successes. So what we have to do is we are going to have a new test statistic for two proportions. So remember, we had a test statistic for one proportion. Now we will have a test statistic for two proportions, and this is the formula. You don't remember, we don't have to calculate this by hand. I will not ask you to calculate this by hand on a test or on, so you don't have to calculate by hand. Because we will have StatDisk so we're going to be able to use StatDisk or your TI 8384. So you're going to be using technology to help you with these. So again, don't worry about the formula if it looks messy. You are not going to be asked to do this by hand. Neither even your P-bar. So what we're going to do is we're going to assume that H of 0, P1 equals P2. So technically this will drop. So P1 minus P2 is going to be 0. That way, technically, what you're only having left over is Z equals P1 hat minus P2 hat over the square root of P bar Q bar over N1 plus P bar Q bar over N2. So technically, this term will drop because P1 minus P2, we're going to assume the null hypothesis is true. So that's going to, your null hypothesis for two proportions is that P1 equals P2. So technically, P1 minus P2, the subtraction will drop. So your Z will drop, your Z test, this part will drop, the P1 minus P2. So technically, this is going to be removed from the formula because we're assuming that P1 equals P2. So this will technically be 0. Now, to calculate the p-value and the critical values, we are going to be using our TI-83, our TI-84, or again, StatDisk. StatDisk for finding the p-value and even the critical values, those are given. We can find the critical values using table A-2, so our Z-score table. So we know how to use our Z-score table by now. Hopefully, we already know that the Z of alpha over 2 is 1.96 for a 95% confidence level, and so on and so forth. So there's a table that we can look for to find our critical values. Now, to calculate our confidence interval, the interval looks like this. P1, so before, when we had a confidence interval for 1, so recall, and I believe this was chapter 7, when we were looking at confidence level, it was P hat minus E less than P hat plus E. This is for one proportion. Now for two proportions, now we have a difference between P1 hat minus P2 hat minus E, P1 minus P2 plus E. So see, look at the difference here. Now you have P1 minus P2, P1 minus P2 hat. And what we're doing, it's a confidence interval. And look at my margin of error. Again, this margin of error is your critical Z-score times the square root of P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2. Again, we don't have to do this by hand. I can show you how to do that by hand. It's very nice. But again, once you know P1, Q1, this can be done using, StatDisk. And hopefully by this time you're an expert using StatDisk. You are obviously allowed to use StatDisk on a test and on a quiz. So you are allowed to use StatDisk. So again, we are going to find using StatDisk the p-value, the pool, the Z test, and everything is going to be given. And I'll show you how to do that. When we're testing a claim about two population proportions, we can do it both ways. We can use the p-value method and the critical value methods. They are both equivalent. Now, the one that's not equivalent, the confidence interval is a method that is not equivalent to the p-value method or the critical value method. So this is not, the confidence interval is not equivalent. The p-value and the critical, so when you're saying, oh, I want a p-value, so we're going to reject if p is less than or equal to alpha, and then we're gonna fail to reject if p is greater than alpha, if your alpha value. So remember, if we go back to chapter 8, and then we saw that in chapter 8. So if I open up my Google Chrome here. So I'm looking at the notes, and it's gonna make me sign up. So remember that we saw back in chapter 8 how we are going to be rejecting the null if the p-value is less than or equal to alpha, and we are going to fail to reject if the p-value is greater than alpha. And then that's when we're doing a p-value. When we are looking at a critical value, we need to see if it's inside the region or outside the region. If it's outside the region, if it's outside the critical region, if what's outside, if your test statistic is outside, if the test statistic is outside the critical region, then we are going to fail to reject the null. If the test statistic is inside the region, we are going to reject the null. So that's the two cases. Those are equivalent. The confidence interval is not equivalent method. Okay. So what we're going to do, let's begin with looking at hypotheses test for 2. This is for 2 proportions. So what we're going to do is we're going to let the null hypotheses, so h of 0, remember that's always equality, p1 is equal to p2. And what we're going to do is that we're going to have the point estimates p1 and p2 are combined to provide the best point estimate for p1 and p2. So we are going to look at also the pooled sample proportion p bar. So then the alternative is either P1 greater than P2, P1 is less than P2, so on and so forth, or P1 is not equal to P2. Those are the other choices for H of 1, right? Your alternative hypotheses. So let's begin with the example. Let's look at an example, and then let's see how we can plug this in StatDisk. Connecticut and New York, so those are 2 samples. Connecticut and New York are contiguous states, both having laws that require front and rear license plates. The proportion, so now there it is, they're giving us the proportion of Connecticut's illegal cars license plate is 239 out of 2,049, or 11%. The proportion of illegal license plates is 9 out of 950, or 1.9. The sample, there's a sample, the sample percentages, so there's P1 hat and P2 hat. One is 11.7%, or 239 over 2949, or 1.6%, or 9 out of 550. They are obviously different, but are they significantly different? So for that, we are going to begin looking at P1 hat and P2 hat, and we are going, it's not given, but they're telling us what to use. Alpha is 0.05. So what we can do is we can use StatDisk right now. So we know that the total sample size, this is N1 and this is N2. And then we have our number of successes here. This is the number of successes, 239 out of, this is X1, and this is X2. Okay, we can find Q1 and Q2. So we can find Q1 hat by doing 1 minus P1 hat, and Q2 hat is 1 minus P2 hat. And then we can use StatDisk. So let's do that. Let me open up StatDisk. And then let me show you how to do that. So very easy. We can just do it in really seconds. So once we know our pieces of information, we're kind of good to go. So here's StatDisk. This is the Triola textbook that we're using. You want to clear out of here. All you need is statdisk.com. You're going to go into analysis. So you're looking at my screen right now, and then you're going to look into hypotheses testing. And then you're looking for proportions of 2 samples. So you're going to click right there. And then we don't have yet we still don't have our our alternative hypotheses, but what we're going to use is, let me go back. Let's go back so then we can identify what our alternative hypotheses is. So right here, they're saying that the sample percentages are obviously different, but are they significantly different? So what we're going to use is that our null hypothesis is P1 equal to P2. So the alternative will be P1 is not equal to P2. So remember, it's always kind of like the opposite of our null hypotheses and what we're given here. They're obviously different, so they're not the same. So they're not saying one is greater than the other. So this obviously different tells us that P1 is not equal to P2. So we are going to be we're interpreting what we're given. So let's go back to StatDisk. So remember, what we need is the alternative hypothesis. So P1 is not equal to P2. That is our alternative hypotheses. Our significance level alpha is given of 0.05. Our sample size for N1, we wrote it down. N1 was 2949. And then we have our number of successes was 239 for Connecticut. And then sample size for New York, N2 was 550. We have that down. And the number of successes, X, was 9. So once we've input this information, we're going to select evaluate. So there's everything that we need. There's our pool proportion. Again, that's P bar. Let's write that down without even having to write anything. So P bar is going to be 0.09542. And then our Z, our test statistic, is 7.10742. Our critical Z value is going to be in between. So there's 1.9. That's our 1.96, our usual. Our critical Z, it's a 95% confidence level. We know that. There's our critical Z value, and there's our P value, 0. Alpha is 0.05, and the P value is 0. Well, what do we know about alpha? So let's go back now that we wrote everything down. So there's our pool. There is our, Z statistic. And then here's our critical value. Now, what we're going to do is notice that we have our P value of 0.00 and we have alpha. Well, P is less than alpha. P are less than or equal to alpha. So 0 is less than or equal to 0.5. That's true. So that means we are going to reject the null. Reject H of 0. So P1 is not equal. Or sorry, you know how we have equality? Reject our null. That means we are going to support the claim that they're obviously not the same. We also found, so there it is. They calculated the Z. They did this manually. They inputted the values. We don't have to do that. because we have our calculator, we found our z-score, sorry, our p-value. So this was the test statistic that we found. But again, you don't have to calculate this by hand. You do have your stat disk. And then we found the p-value right there, which was less than. So then what can we say? Our test statistic is inside the region. This is a two-tail. There's our test statistic. We are going to be inputting the fact of 1.96, the positive, the negative. So let's say if this is 0, negative 1.96, and then we have 1.96, we're going to shade the region. And we identify the test statistic is inside my region. That means, again, we are going to reject the null. So in both cases, we're supporting the claim. So because the p-value is less than alpha, we reject the null of p1 equal to p2. So what does that tell us? What is the interpretation here? We must address the original claim. Connecticut and New York have the same proportion of cars with rear license plates only. Because we reject the null, we conclude that there is sufficient evidence to reject the claim that P1 is equal to P2. That is that we have sufficient evidence to conclude that New York and Connecticut have different proportions of cars with rear license plates. It's reasonable to speculate that the enforcement of license plate is much stricter in New York than it is in Connecticut. That's why Connecticut's car owners are less likely to install front license plates. So here we can use, of course, stat disk, which is everything that's given. There's the pool, there's your test statistic, your critical value, and your p-value. And they finish off. So if we go back to the value, there's our confidence interval that we found. So notice that 0.05, if we look at alpha, 0.08 and 0.01, alpha is a critical value. And what do we notice here? That technically we do have 0.05. See how this one is 0.08 less than P1 minus P2. Notice that 0.05 lives in this region. So let's write that down. So they went ahead and substituted Z of alpha over 2. They found the error. Here. So we know that the critical score is 1.96. Then you substitute P1, Q1, there it is. P2 hat, Q2 hat. Remember we got this from the table. P2, this is P2 hat, Q2 hat, 1 minus P1 hat. And then they plugged this in the calculator and they found the standard error. Remember, to find the answer, you have to do P1 hat minus P2 hat minus E, P1 hat minus P2 hat plus E. And they found this answer. But we already had found the answer using our stat disk or TI-83 or TI-84. So to do that, what do we notice? Well, we notice that 0, so the null hypotheses do not contain 0. See how this is actually greater than 0? So the confidence intervals do not contain 0. So that means our null hypothesis does not show up here. So there is not a 0. That means that we have sufficient evidence to reject the null. Same thing here. We know that alpha is 0.05. Well, 0.05 lives in here. Okay, see how 0.08 is greater than 0.05, which also is outside this region. So then here, what can we say? Well, the null was P1 is equal to P2. That means that P1 minus P2 is equal to 0. But 0, it's not. It doesn't show up there. It doesn't contain it. Okay, that means that there is a significant difference between the two proportions. So let's highlight that. Since the confidence interval does not contain a 0, that means that there is a significant difference. If 0 was contained, then there's not a lot of a difference, but in this case, it does. So what do we do when the requirements are not satisfied? Either you have bad samples, and then you also have the requirements that each of the two samples have at least successes and at least 5 failures. Then we use another test called Fisher's exact test. We don't use that in this class, but that's another alternative. So remember that at the beginning, the requirements was n times p has to be greater than or equal to 5, and n times q must be greater than or equal to 5. So you have to have at least 5 successes, at least 5 failures. So if you violate these requirements, we also can use the bootstrap sampling method, which was in 7.4 that we didn't do. So we're not using these. So why do the procedures work in this section? And the reason why is that P1 can be approximated by a normal distribution mean P1, standard deviation variance. Now the difference P1 hat minus P2 hat will also approximate by the normal distribution mean P1 minus P2 and the variance. So the difference is that the variance of the differences must be two independent random variables. And that the random variables is the sum of their individual variances. Again, this is what we're going to do in the preceding sections. Okay, so we have all of this works because of normality. It must be a normal distribution. Okay, with a mean of P1 standard deviation of the square root of P1 times P2, the square root of P1 Q1 over N1. Same thing with P2 and Q2. Now, in the preceding variance, what does it lead to? How do we find the variance? And this is calculated by the differences between the two sample proportions is equal to the square root of the pooled P hat times Q hat over N1 plus P hat times Q hat over N2. So we know that the distribution of P1 minus P2 is approximately normal. P1 minus P2, the mean is also normal. And we are going to be using the z-test statistic from earlier to identify this. So why do the procedures of this section work? So when we're constructing the confidence interval estimate, the difference between two proportions, we don't assume that two proportions are equal, and we estimate the standard deviation, though this is going to be the estimate of a standard deviation. So if we were trying to calculate the standard deviation of two proportions right here, P1 and P2, let me change this to P1 minus P2. If we're trying to find the standard deviation between the two proportions, we would use the following formula. Okay. Again, we know the test statistic. We use the test statistic for the two sample proportions. Again, this will be using StatDist to calculate the Z statistic for two populations. So we're going to be using both positive Z-scores and negative Z-scores. And we're going to be looking for the two-tail. So remember, we have two-tail test right here when we are looking at both positive and negative values for those. And we're also looking for the critical values when we're shading, if it's inside the region or outside the region. And with that, we finish section 9.1. It's pretty nice and straightforward. once you know how to use StatDisk. So StatDisk will be a lifesaver for chapter 8 and chapter 9. And I'll stop the recording now.